Hey, hello everyone. So welcome to the Quantum Business Seminar. So we are happy to have Wojtek Fedorko from TRIUMF to be our speaker today. So Dr. Fedorko completed his undergraduate study at the University of Toronto in physics and mathematics and computer science. So then he completed his PhD in physics at the University of Chicago. So at Chicago, he developed a real-time data processing system and studied the properties of the top clock at the CDF experiment at Fermi Lab. After that, he joins Alex experiments with fellowships and do a postdoc at CERN, Michigan State, and UBC. So he now returned to Canada. He is serving as the TRIUMF Deputy Department Head for Scientific Computing, concentrating on machine learning and quantum computing applications to many branches of science pursued at TRIUMF. So I think he is now telling us more about the quantum science in TRIUMF today. It's your stage.
Thanks a lot. Thanks very much for the invitation. Very nice to be here and to have chats with several colleagues here. Yeah, so thank you again. So a lot of you might not know all the details about TRIUMF. So I'll start with a quick introduction there. We are on the other end of town. I think similar altitude above sea level. This is our campus here. We are very happy to be on the traditional territory of the Musqueam people. So it's also a beautiful site.
Not today, not today.
Wow. Oh, okay.
It's another type of beauty.
It's always beautiful. It's just a matter of clothing, I think.
Okay.
So our lab is home of about $1.5 billion in infrastructure investment. We are doing a whole range of science, nuclear, very rich nuclear physics program on site, some particle program on site, also material science, life sciences, and accelerator physics itself. And what we really are is a facility for universities or hub for universities to join big science projects and global experiments such as one at Atlas at the LHC, Large Hardon Collider, NA62, Alpha at CERN, Large Neutrinos experiment in Japan. We do a lot of detector development, also accelerator development, of course. We produce isotopes for cancer treatment and diagnostics. We have a commercial facility. If you want to send your electronics to space, you can come to us and simulate that environment and radiation. We have about 600 people. We are more than 50 years old, and the hub of our infrastructure is the cyclotron, and which produces 500 protons and then drives primary beams, which are then used to produce a bunch of secondary beams around the site. There's also a bunch of smaller cyclotrons, mainly for medical sciences. Yeah, out of this cyclotron, you can produce, well, it shoots out protons, but secondary beams include muons, and then a whole rare isotope facility here, and also stable isotope facility here, which is going to be now, the rare isotope is going to be now expanded with Ariel project, which is going to provide about factor of 3 more beamlines. So again, the core of the infrastructure is the cyclotron. Okay, so switching gear in terms of what TRIUMF actually does in this quantum space, and I'll start with quantum sensing, and which is not really my area of expertise. So all mistakes and misconceptions are mine, and I thank a lot to my TRIUMF colleagues who shared a lot of information with me in preparing the seminar, but you can blame me for the mistakes. So I'll start with the efforts in quantum sensing, on how we're using quantum sensing to drive some of this fundamental and applied science, and then I'll switch gears and talk a bit more of the application of quantum computing, where I'm directly involved in a specific particle physics application. Okay, so quantum sensing. What's quantum sensing? Basically, there are some kind of criteria. We have to have a quantum system which has some resolvable energy levels. We must be able to initialize that system in a well-known state, then and manipulate that system, and the quantum system has to be some kind of sensitive to whatever effect we're trying to measure, be it magnetic field, some kind of magnetic electric field, laser light, and it can have many effects. Maybe it's going to change your angular state or energy levels, or maybe generate some kind of frequency shift and transition probabilities between the states. So there is a lot of things we can do with this sort of a toolkit to attack fundamental science. And at TRIUMF, we are basically doing several of this kind of experiments, and I'll focus on 4. There's a whole, they are really mainly driven by TRIUMF colleagues, but behind each of them, there is a international collaboration. So BEAST experiment with beryllium electron capture, radioactive molecules, alpha and alpha G experiments, and also the ultra cold neutron. I'll focus mainly on those first ones. Okay, so motivating how we can do, why we want to do this. Standard model is known to be incomplete. We know that there is multiple kind of mysteries inside there, and one of the purported extensions of the standard model is hypothetical presence of sterile neutrinos, which those can have masses on keV scale, which would be a great candidate for dark matter, and they are sterile because they are not interacting with standard model forces. But we can probe that sector by mixing with active neutrinos. So those are no bread and butter sort of known neutrino flavors: electron, muon, and tau neutrinos. But they're possible. It could be a mixture of a sterile neutrino in there. And this experiment, which already has results and putting limits on models, is this BEAST experiment. So it turns out that if we use beryllium 7 isotope, and which decays with a beta decay through electron capture into lithium, because this this flavor state is an admixture of mass. Sorry, this mass state is a somehow mixing of the flavor states. It turns out that the recoil of the lithium nucleus from the emission of this neutrino will be actually affected if there are more flavors of neutrinos out there. So the whole purpose of this experiment is to measure this recoil energy of this lithium nucleus at a very high resolution. So with resolutions of about electron volt. So there is a definite advantage. We have a relatively large decay energy, and it's a pure two-body final state. But we need very, very high precision recoil measurement. And this is done in this kind of a process where at TRIUMF we have those kind of superconducting tunnel junction chips. At TRIUMF we are irradiating them with a beryllium beam, basically implanting that microcurie type radiation level into the chip. We send them off to Lawrence Livermore, where basically they can measure, and I'll talk about it in a minute, measure the recoil energy of the lithium very precisely, and perhaps measure the shift that you can get. So you can see that under standard model, you basically get this black expectation, and if you see a little bit of a shift in the spectrum, so this is signal, but when you overlay, all you see is this kind of slight deviation to the spectrum. Perhaps you can you can put at least limits or observe it. The way it works is basically you have this the superconducting tunnel junctions arranged horizontally, but it's kind of depicted here vertically. So when you put a bias in the junction, you actually can end your radiation or recall energy, deposit some energy here. You produce basically those quasi particles. You break a Cooper curve, but the so-called quasi particles can tunnel through the bias that you have induced, and you can measure that current, and from that you can deduce the recall energy of the lithium nucleus. So it's definitely a measurement that uses a lot of quantum physics in there to perform the measurement. So, and switching gears a bit to the radioactive molecules, the simulation, the motivations is kind of similar. We know that we need to generate more CP violation that we have in the standard model to basically generate preponderance of normal matter over antimatter in the universe. Why we are here is that because there is a very, very tiny imbalance in the production of matter and antimatter, which we cannot explain under the standard model. So the purpose of this experiment is to really target that and check if we can measure this CP violation. And this is this experiment is partially funded, but it's it's still in a planning phase or startup phase. Basically, the whole concept is to use those so-called pear-shaped nuclei, i.e. nuclei with high octupole moments, to measure their so-called shift moment. So shift moment is a combination of different dipole, quadrupole, octupole contributions of the structure of the nucleus, and turns out that it basically comes out if you write down the potential of electron around the nucleus, you can kind of separate the contribution from the nucleus and the electron, and the shift moment is the kind of the nuclear contribution. So in those octupole deformed nuclei, the pear-shaped nuclei, this shift moment is quite a bit enhanced. So this makes a huge kind of enhancement factor over what's possible to measure in the kind of gold standard nuclei, in mercury nuclei. So the plan is to create this kind of a molecule, because also we have a problem with the screening of the dipole moment of the nucleus. So we get around that this way, and basically measure nuclear electron dipole moment, electric dipole moment, which basically impacts the shift moment. And then if we measure deviation from the standard model prediction, then it's an indication of some sort of new physics that gives us that. So how this is practically planned to do, and why is it a quantum sensing experiment? We basically can trap those molecules, and then the first stage of this the milestone there would be to basically drive all the populated states. So all of those low energy states will be populated thermally, and the experimenters here are planning, have designed a whole scheme of how to drive through laser and microwave manipulation of the states, so driving the states different ways to basically try to populate this lowest state, and then basically through dissociation of this molecule. So you drive first to from this from this J equal 1 state, you would drive it up to another state and then apply a pulse to dissociate molecules, and then the thorium escapes the trap and can be imaged on a multi-channel plate. So basically, you can count the population of thorium ions here. And so this is only a kind of a demonstration phase, but in fact, where you would see the, they call it the physics state, but this is actually split in due to hyperfine structure, and then you get the shift moment will generate actually splitting in those or shift in those hyperfine energy levels, and you would measure some basically a different population oscillation if the shift moment is there. So that's how you can hopefully discover this. Going into alpha and alpha G, which study basically anti-hydrogen. So why would we want to do it? We can measure basically asymmetries between the, again, it's kind of fundamental symmetries in the universe, antimatter symmetry. One of the questions is, does antimatter behave identically than matter under gravitational interaction, which would basically be CPT violating if it didn't. So it's again attempt to address fundamental physics questions. And the apparatus is at CERN using their antiproton accelerator, and basically they have two traps, alpha 2 atom trap and alpha G. So this experiment has been used for roughly 15, 16 years already to make various anti-hydrogen spectroscopy measurements. And this one somewhat recently has been used to test the interaction of anti-hydrogen under gravity. So yeah, precision spectroscopy, laser cooling, and then gravity measurements. So a bunch of state transitions have been measured in this alpha 2 experiment, driving those hard to observe transitions. I'm really not an expert on this, but there is a lot of spectroscopy measurement basically done here, and this is more recent result where they use this alpha G apparatus to first create and trap anti-hydrogen atoms and then release them, and you measure gravitational interaction under this. So where this is heading, and this is going to be hosted at TRIUMF. Both those previous experiments are basically a magnetic trap, but you basically have a almost 100% non-homogeneity in the field, and it's also very hard to develop techniques in this sort of setting. So a proposed experiment at TRIUMF is called HYCO, Hydrogen Infrastructure experiment. So the idea here is to basically make a hydrogen fountain, which has not been achieved before, and uses a proxy to develop techniques for anti-hydrogen experiments in the future. Ultra cold neutron atoms is also a facility that has had a lot of success with first beam late last year, and it relies on basically a ton of quantum effects to perform this. Again, the main idea behind this experiment or this facility is to enable EBM measurements and try to get that new physics that way. So now I will try to change gears a bit and talk about quantum computing projects, which is more or less led by myself and my colleagues. And the idea here is to address a very specific question or specific technical and computing problem in particle physics. So this is a kind of a so-called event display in a big experiment at CERN called ATLAS, where the particle beams collide, kind of going into the screen there and produce jets, which are those kind of clustered into this conical kind of logical shapes, bunch of tracks coming out, and then particles hit the calorimeter, and the deposits are indicated by those kind of columns. So bigger the column, the more energy that calorimeter cell receives. Calorimeter is basically a device that stops the particles and measures the energy. And we need to have a lot of these sort of simulations to be able to interpret the data coming out of the ATLAS experiment. Basically, you're doing hypothesis testing, whatever you want to measure, be it, let's say, a Higgs coupling to itself, which is the canonical measurement at high luminous TLHC, or whatever you want to measure. You basically need to create a lot of simulations of that process, also diagram processes under different hypotheses of how your detector behaves, i.e. your systematic effects, and then run it through kind of first principle simulation, which creates this kind of what we call the hard scatter process, and then walk all the daughter particles through the experiments and through the interaction of those particles and secondary particles with the experimental apparatus. And so why this is hard? Because every single primary particle that hits your calorimeter will create an electromagnetic or hadronic shower of hundreds or even thousands of secondary particles. And your computer has to basically keep track of all those secondary particles as the shower develops, model its interactions with the material detector, model how your electronics responds. And that's why this process alone for a single particle takes about a second on a CPU, and you have hundreds or thousands of those primary particles in a single event. So you can imagine that we need a lot of that stuff going on. Exactly how much? This is a graph that shows you progression in years, and about the end of the decade, the projected usage under different scenarios goes up, and the scale here is in millions of CPU years annually. Right, so we're gonna be consuming, if we don't change anything, we're gonna be consuming millions of CPU years and doing it, for a decade plus. So clearly, the business, as usual, is not sustainable, and this shows you how much of that computation is dedicated to this sort of simulations that we're talking about. So simulations of particles impacting our calorimeters, and that's a size. There is no single silver bullet, but it's a very sizable chunk of the pie. So,
ask a quick question.
Sure.
The red one there is dramatically lower.
Yeah. So people are working aggressive R&D and conservative R&D scenarios, right? So like there's always some R&D that has to happen, and people are working on all sorts of fronts, right? So there's groups of trying to accelerate the hard scatter collision on let's say GPUs, or maybe there is even people working on quantum computing application in that simulation. People are trying to, and colleagues here, this if you are maybe trying to improve tracking, particle tracking, which will go under the reconstruction in this graph. So basically this pi and this pi, right? So there is whole teams of people working on many R&D projects, and there are assumptions made in the graph of how far will they get, how successful they will be. So those are different scenarios. And going back to this simulating calorimetry challenge, this is a very known problem, and so there is I would say probably about 20 groups around the world trying to attack this with generative modeling, generative machine learning, and our twist is to try to do it with a little of a quantum computing secret sauce. So we're using this in this talk. I'll unfortunately cannot tell you about internal atlas results, but I'll show you what we have with the publicly available data. So we rely on this open data set where we basically simulate single particle interactions impinging on our calorimeter. This is about just under 5 Moliere radius, so capturing vast majority of the shower. And in terms of interaction lengths, it's a many interactions length. 36 interaction lengths. So basically, there is no chance of shower kind of escaping this this volume, and highly segmented. We have about 6,500 voxels in this little volume of simulated detector. So why do we think quantum is applicable in this project, in this problem? And the idea is that in let's say most accepted classical generative AI models, they work on the principle that you start with some sort of easy to generate random distribution. For instance, a multidimensional Gaussian. So you can very easily generate this sort of distribution. It's a multidimensional dice, basically. But once you have a random number from this distribution, you have to apply a long sequence of deep learning operations, basically, on that number to finally get the data in a form you needed that actually looks like the data you want. So it can be celebrity faces or fake videos or whatever. In our case, it's calorimeter showers. But this process itself is really expensive, and that's why you cannot get those chips, and we are pouring some unbelievable amount of energy in all those LLMs and synthetic videos, right? That's the difficult part. So the main idea behind our approach is that instead of generating a simple distribution, we're going to start with already a complex, expressive random number distribution, which we will teach the model to be in some sense optimal for generating this process, such that we only need to apply a short, a very modest deep learning architecture to decode this distribution into the data that we need much more directly. And the whole point that it's not just arbitrary distribution, it has learnable features. So we can teach the QPU, the quantum processing unit, to generate from an interesting distribution for us. We start with a very well-known and dated deep learning model called the variation autoencoder, and we'll build on that. And this is something that's been developed before we joined the Spider project. But basically, you take your data in this model. You have some kind of encoder, or we call it approximating posterior, to generate two vectors of means and rows, and then you generate a random number from a normal distribution. You multiply your sigmas by the row and shift by mean to generate some number z in this so-called latent space. Now, once you have it, you can decode it back into the representation that you would like. And you teach this model by basically comparing the output to the input. You cannot directly estimate the log likelihood of the data under this trained parameters data of this model, but you can bound it from below. That's called evidence lower bound. And it turns out that it kind of breaks down into two pieces. We basically require that this latent space follows some distribution, and the easiest way to do it is to require that this follows a normal Gaussian distribution, so n0, 1. And if you require that, you can basically analytically derive the form of the loss, and it breaks down basically into this minimum square error loss, which compares the output to the input, and this Kullback-Leibler divergence loss, which compares how far your encoded number from your encoder follows this prescribed distribution. So this is a very fast architecture, but it doesn't work very well in practice because the latent space is not learnable, like you're assuming what it has to be. Yeah, it's not very expressive. You have a very basic distribution there. So in practice, basically on all tasks, it doesn't perform well. So next idea how to improve this is to put a very expressive latent space inside this model, and we're going to be using a restricted Boltzmann machine. So restricted Boltzmann machine is a universal approximator to binary distributions. Now our latent space is 0 and valued rather than real valued, and has this kind of bipartite structure. It's an energy-based model, so we can write down the probability of drawing a state from this latent space according to this Boltzmann distribution, and then we the energy is described by basically the coupling between the left side and the right side, and also the biases on the two sides of this model. So this is a much more expressive generative model. In fact, it's arbitrarily expressive. We can show that with sufficient size, of course, which is another story, but a restricted Boltzmann of sufficient size and connectivity can in principle model any arbitrary binary value distribution. So it's a much more powerful model, but you have to pay for it. To sample from it is not easy. It requires Markov chain Monte Carlos, basically. So we're kind of back in square one. I should also mention, I mentioned before, that to train those models, we need to basically backpropagate. So we need to estimate the gradient of those losses under the gradient of the loss with respect to the parameters of the model, theta and phi denoted here, and also in case of the RBMs, also with respect to those couplings and offsets. And to do that, that's very simple in this case, but it gets complicated while we have the RBM. But it's still possible, but we need to do sampling. So a nice validating fact here is that this RBM setup was actually part of the Nobel Prize, and Geoffrey Hinton was one of the contributors to development of those sort of models. So it's kind of interesting that we are looping back to those sort of developments. To backpropagate through, we need, in case of the VAEs, it's very easy. We just need to do this kind of shift and scale, and then you can estimate the gradients. It's a bit more complicated for the RBM, but it still can be done. So in this case, we basically generate this vector rho here is a uniform random number, and then we apply this kind of relaxation trick where we basically our encoder network outputs logits, and then we reparameterize using the Heaviside function like this. So instead of the shift and scale, we basically apply this transformation. So this is a Heaviside function, which is a step function, right? We have our logit, so basically a real valued number. We shift the inverse sigma function by this logit, and that's how we can generate basically generate the same binary variable. So one additional thing that you need to do is to estimate the gradient is to relax it into a smooth function, right? So instead of heaviside, we replace the heaviside with a sigmoid with some kind of temperature function, which basically describes the smoothness of it. So in the end, what you need to do is to, you generate your row, you apply the inverse sigmoid, so you read out where you have landed, you shift it there, and then if you finally turn down the temperature during your training, if you find you're on the left side or right side of this step function, that's how you decide if you should have a 0 or 1 there. Okay. So taking a little note, why is it so difficult to sample from this and why we need quantum computing? Basically, the sampling, and this is also why you need this kind of restricted structure. So it turns out that if you fix one side of your Boltzmann machine and under a certain set of weights sample from the other side, all I need to know is those kind of Bernoulli weights here, right? Because the node here only depends on the other side, but it doesn't depend on there's no connections within a layer, right? Only to the other layer. So it turns out that if I do conditional sampling, that's very easy to do. So if I have two random variables and I know how to sample this conditional distribution and this conditional distribution, if I alternatively sample them, which is shown for a Gaussian, but it was the same for binary variables, if I switch back and forth, it turns out that the distribution will converge in distribution sense to this Px of y, the joint distribution. But again, it's a super expensive process to do. So pain, but can be done. So how can we do this with quantum annealing in this case? This is the Hamiltonian of a D-wave quantum annealer. You have two pieces there: initial Hamiltonian and final Hamiltonian. So you basically prepare the state in a ground state of sigma x, but which is a superposition of sigma z, and then you start with the high A and B equal to basically 0, and through the annealing process you drive A to low value and you drive up B to a high value. So in a kind of a canonical optimization use case of this QPU, you want to basically start with in a ground state. And the theory is that if you do this slowly enough, you stay in the ground state. And if you can map whatever your optimization problem is, let's say assignment of nurses to station, hospital, or trucks in a harbor or whatever, if you can map that problem onto the problem Hamiltonian and you manage to stay in the ground state of the Hamiltonian, voila, you have just arrived at an optimal solution. So that's like a first level picture of what's going on. But what's actually going on is that the system is in a thermal bath. So it has some kind of a Boltzmann distribution of the state. So it's basically quantum sampling. We're doing quantum sampling of thermal sampling of a quantum system, right? And probability to discover the system after the anneal is basically has the same form as we saw just a couple of slides ago. Is proportional to the energy of the state. So the higher the energy of the state, the less likely you're going to find it exponentially. So we actually exploit this, and we're going to use the D-wave device as a sampler, and this is very fast. This occurs in about 20 microseconds. So our use of quantum device is basically to get away from the Markov chain Monte Carlos. We have to do a little bit of work. So we need to respect the graph of the device. The D-wave device has evolved over time. What we want is to have this kind of a graph, but what in practice we get before the latest architecture was a 2-partite graphs, but now those have evolved into a 4-partite graphs. So we need to map basically we are constrained by this sort of architecture. So we try to directly, at this stage, directly use this graph in our training. So we need to basically account for the connectivity there and design similar process to the standard Gibbs sampling, but we now do a kind of a round robin sampling where we fix, let's say, 3 layers, and then we go in a round robin sampling successively from each of the layers. There is a mapping, natural mapping between weights and biases of the RBM to the couplers and offsets in the QPU. So we can basically transform the Hamiltonian of the RBM to the Hamiltonian of the quantum annealer back and forth with a constant offset, which then doesn't affect the probability of states being drawn, so it can be ignored. There is another hitch that we need to get through. Basically, during training, we assume that our KBT is equal to 1, which is not the case on a real machine, so we need to correct for that. And also, it turns out that there's some kind of freeze-out effects where not only the physical temperature of the QPU matters, but also effective temperature is kind of apparent, and we get rid of both effects by effectively scaling our biases and weights by some kind of effective inverse temperature beta star. And in principle, this is unknown. So what we need to do, and this is a little bit perverse, is that we actually tweak this beta star until the distribution generated from a quantum annealer matches that distribution generated by classical sampling. So in future we may be able to get away from it, but right now we're using this sort of iterative method. So we still rely on the Markov chain Monte Carlos to basically discover the effective temperature of the QPUs. So these methods have been described earlier. Basically, if you start from the assumption that you want to minimize the divergence between the probability distribution generated by the annealer and the classical RBM, if you basically make a statement that I want to minimize this divergence, it turns out that you can derive this sort of an update rule where at some step t, at t+1, I would take my previous best estimate of the temperature and then compute those kind of averages. So it only relies on the average of the Hamiltonian. So basically, you take some samples from the quantum annealer, you compute their energies under the Boltzmann machine, you take some samples from the Boltzmann machine, you compare the means of the distribution, and you try to minimize this through this update rule where eta is basically your learning rate. And it turns out that after some time, this converges to a stable value. Now, what we have done is actually improve on this a little bit. And instead of taking the difference, which basically comes from minimizing probability divergence, if you try to equalize entropy of those two distributions, so distribution generated by the quantum annealer and the RBM, basically you get this sort of an update rule, which is amounts to finding a fixed point of this mapping, and you can actually scale it by beta, which can be adapted. So you can try to get to the to matching again of those averages. So in practice, you're still doing the same. You're taking samples from quantum annealer. You took already some samples from the RBM, and you continuously comparing them. But you can drive down the time it takes you by modifying this delta. And this is just a quick illustration of how this works. So the samples taken from an RBM, which you only need to do once, fortunately, are in this open histogram, and then the quantum annealer samples after different assumptions of beta, which is evolving, eventually collapse onto this distribution. So it works quite nice in terms of the how the model actually looks. So our deep learning architecture is kind of a hierarchical autoregressive architecture. We have our data, so this is our shower data. We want to condition it on the energy of the impinging particle. And I'll tell you a little bit about it in a minute of how we do it. But basically, our encoder is conditioned, so we pass the data successively and generate different what will end up our partitions in the QPU. But we generate several segments of this latent vector. We also then train simultaneously the RBM. So the RBM is basically spectating on this data and try to learn it by minimizing the divergence between the distribution generated by the encoder and the distribution generated by the RBM under sampling. There is, in the decoder depicted here, there are basically two heads, which is also kind of our secret sauce. We generate activation vectors, so we tell the model, basically tells, is this voxel activated or not? And if it is activated, what's the energy in that voxel that we have observed? During generation, we basically do the same. We're conditioning the RBM and then generate the rest of the latent vector. We pass both of them for just this decoded piece and to generate our data finally. Okay, so there is we've done a lot of development on how to condition the model. So specifically condition the QPU to generate the data that we need. So just like in a synthetic image generation, let's say, you would want to not just generate, let's say, a face, but you would want to tell the model, okay, I want a face and has to be female, blonde hair, sunglasses, please, right? So those are conditioning variables. So we want to tell the QPU, okay, let's generate a particle with a specific energy. Right now we're only conditioning on one variable, but it's quite important that we have the capability to do that. So we do this through this flux bias mechanism. So we've seen this Hamiltonian before. We have our sigma x term, our initial Hamiltonian, our problem Hamiltonian. But what the QPU actually does is implement this sort of Hamiltonian with a bunch of fluxes here, which depend on the drive current and the annealing variable S. And if you look a little bit carefully, this term here is basically expanded into this term here now, right? And this flux here appears linearly in front of the sigma z, but appears with a square in front of the interactions of sigma z ij, sigma z I, sigma z j. So to basically balance that out, the D-Wave introduced this additional flux sigma xi. So that's the flux bias, and this has to have a specific form, which basically then matches this quadratic form. This is done so that our factors in the problem Hamiltonian, h and j, stay at the constant ratio. Otherwise, they would have different ratios through the annealing process, and you would not be solving the problem that you want to solve. So we hijack that mechanism basically, and for selected qubits, we're going to drive that flux bias very high or very low to basically guarantee an outcome on a subset of qubits, which are our conditioning qubits, to be matching our conditioning variable. So we encode the energy of the impinging particle in some kind of a latent code, some kind of binary code, and we fix one partition to that code through the annealing process. So we basically are not allowing a subset of our QPU to evolve at all. And through the couplings to the other qubits, they basically generate now a conditional distribution, conditional Boltzmann distribution. Okay, so how does this work? This is just a test of the restricted Boltzmann machine energy and this ground truth. So we basically pipe our training data through the architecture, and we ask our RBM, okay, what's the energy of this sample under the conditioning, and then we do this classically and on a QPU. So that's just a basic test that broadly it matches. We test a bunch of just heuristically looking at those kind of images, and they have a nice variety. We test a bunch of physics variables, so let's say energy per event under just reconstruction, so just passing the samples through the architecture under classical sampling and under QPU sampling. So this is energy, this is so-called sparsity, so how many boxes were hit or not. And we look at a bunch of other distributions under conditioning. So we take small slices of the energy of the particle that's impinging on the calorimeter. That also looks very nice, but at some places it could be still improved. We look at a bunch of physics metrics. So this is a whole field. So this is like 17 other groups that are publishing results in this field with classical generative models, and they're publishing this sort of metrics called kernel and Fréchet distance. So basically, it's kind of a score, but it's not a normalized score. So lower is better. The ground truth, so like if you pipe the ground truth through this metric, you can't do better than that, right? So this is bounded here, and it's a log scale. So we're actually pretty good on because it's a log scale. There's a lot of people behind us, right? So it's a very good. It's a very competitive model basically, in terms of quality of the samples it generates. And those are kind of energy estimates of our model, and those are super crude. That's why the little grain of salt right there. But basically, under some number of assumptions that we make here, like an A100 GPU will eat 400 watts flat out, but the QPU is like some milliwatts or whatever, but the dilution fridge is 16 kilowatts, right? So you have to be a lot faster to go down to competitive energy consumption. We are a lot faster, so we are not even on that graph. This is a time per shower, and for all of those our friends and competitors under different CPU or GPU, how big the batch they pipe through it, etc. So we're much better than any of those models. But when you go joule for joule, we are not bad, but we are not as good as some of the. The upshot here is that the better the model is, so like a diffusion model, is not even competitive with ground truth, the first principle simulation, right? And we are somewhere here, so we are better, but maybe there are some, we are in a ballpark basically. But this has the assumption that we have solved a lot of engineering problems around the sampling problems, which I will not get into it, but it's not completely fair because we have to deal with readout, we have to deal with QPU programming and all those kind of facts. So I just want to thank all my collaborators that contribute to this problem. And we are now working on the Atlas data set. We're making a lot of progress on how to address the QPU issues, how to be more efficient with conditioning and all that. And I will just close out with one other item, that another place at TRIUMF where there's a lot of like quantum sensing of materials is beta NMR and USR program. So basically, in those programs, you implant a spin polarized ion or a muon into your sample, and then this acts as a quantum probe of the magnetic environment of the material. And we do a lot of, we are basically one of a handful of facilities around the world that does this. So it's really a unique capability. We're studying a lot of very interesting effects, superconductivity, exotic material states, fermions, etc. And I really think those two things can, and a lot of non-quantum materials for life science specifically, but also battery and biological systems. And where I think those two kind of streams can converge is really trying to implement a real simulation for real materials of interest. So for instance, quantum spin liquid candidates, quantum spin glasses, where we may be able to model this sort of real system with our magnetic probe implanted. So basically implementing that type of a Hamiltonian on a QPU, letting it evolve using and all of this using new capabilities of those processors, for instance, arbitrary state preparation, multicolor annealing, and all that. And I think maybe it's also possible to do on ion traps. I believe it could be done as well. But the long-term goal is to use the data that we already have, or maybe take some more data from those facilities and develop a verifiable simulation of real materials, which in the long term could enable optimization design. Okay, so I stop here. Thank you very much.
Interesting talk. Any question from the audience? Oh.
Hi. Two questions. What goes into designing, I guess you'd call it the encoding layers? If you showed 4 there, so you have 4, and you mentioned that you'd like something very short rather than these long ones that become the typical way of doing it. You have a trade-off in terms of the QPU size.
Yeah.
How do you decide that? And the other question was the flat scaling that I just saw an advantage of this approach in one of your final slides.
Yes. So the I forget where I put this flat scaling, but basically the okay. So addressing this first question of how do we do the coding. So and actually in the most recent development, we went back to the bipartite graph, and we're using chains of qubits to encode logical qubits. That allows us to actually implement a fully connected bipartite reciprocal bottom machine on a QPU with sufficient. It turns out it's sufficient size to model the complexity of the data that we have. And how the conditioning becomes more efficient is that we only need the chains for real kind of working qubits. So the qubits really participating in this in the quantum annealing. We can use the kind of leftover qubits that we cannot chain anymore on the QPU, and we basically because it's a static thing, so we can drive those qubits. It doesn't matter that we drive the same, several qubits to the same state, because they don't talk to each other. We just kind of force them to be in the same state. An additional component is, which turns out to be really important, is gray coding. So I don't know if you're familiar with that. It's a basically any binary number can be encoded in such a fashion that going from one number to the next only implies a single bit change, single bit flip. So like in a normal binary code, sometimes you have those cliffs where, let's say you go from, 1, 1, 1, you add an additional 1, and then you have 1, 0, 0, 0. So a lot of bits suddenly change, right? This avoids this sort of problem, and this turns out to be much more learnable by the RBM. So it's much more well behaved. So that helps us a lot. And we have to do this going to the future. We have to do this much more efficiently from the hardware perspective, because right now the changing all those conditioning qubits, changing all those flux biases, basically requires a full reprogram of the QPU, which is totally non-efficient. You inject a ton of heat into the QPU, you change the temperature, and it's just not practical in the long term, right? You would never be able to run in production that way. You use much more energy than you can afford. So that needs to be addressed on the engineering side. That's for the future, for sure. And yes, the constant time. So basically, unlike in a restricted Boltzmann machine, a classical sampling, basically the mixing time of those Markov chains depends on the complexity of the distribution you want to generate. The more multimodal distribution generally requires much longer burn-in times and Markov chains. In the thermal sampling of a QPU, a sample is a sample, and you naturally sample the correct distribution and you make your QPU twice as large, you're still going to have the same annealing time. Your readout time might change, but the sort of the basic process is the same.
Yes.
Yeah, you can potentially generate more complex distributions, make them more and more powerful, make the quality of the physics quality of the samples better.
Another question? I think I have a similar question. That's what kind of improvement of the D-Wave machine can actually improve your algorithm? Just like more entanglement, more qubits, or more connectivity, so what kind of thing?
More connectivity, longer capability to generate coherent longer chains. So the longer the chain, the more probability of chain breaks. So like some of the qubits in your chain go one way, some of the other go the other, right? So there's a whole science behind how strong you should make this chain coupling with respect to the weights of your model. We are right now just yanking that all the way up. And that turns out to be a simple approach for us, turns out to be the best, but it's maybe not the most well principled. But the ability to make those chains longer basically would mean that we can encode a larger graph, a larger bipartite graph on CPU.
So the longer chain means that it's a longer coherence time of the.
I will punt on that. I don't know if that's exactly directly related.
Okay.
I don't want to say something wrong, but I'm not sure if there's a direct connection. But in a more let's say basic development, D-Wave demonstrated what they call coherent quantum annealing, right? Where it's no longer thermal sampling basically of the quantum system, but coherent sampling, right? So it would be great if math was developed for that, because like we can do it, but I don't know, I don't have the math to train them all under this condition. So that would be cool if we could figure that out, basically, because then we could directly train on a QPU. And yeah, the other engineering problems are that we need to figure out how to better condition the QPU and how to faster read out the QPU, because otherwise we're just not going to be competitive even on dollar for dollar or joule for joule basis with the classical.
So in terms of
better classical models.
So in terms of dollar, that you show the energy consumption. So in terms of dollar, is that much more expensive right now for the D-Wave machine than the classical GPU?
Actually, no.
Okay.
But we are academic users, so I don't want to prejudge the final application. I believe it would be competitive in terms of how many GPUs you would need to buy and operate. So this was a sort of a simple comparison one can do at the back of the envelope without really understanding all the economics, and this is constantly changing. So it's really hard to do something that has more than a month lifetime.
The GPU is more expensive, so
yeah.
Any other questions? Let me check if there's any question from the Zoom. Oh, there's a question from the Zoom. Let's see. So there's a question online. It says, is there any potential of using this alternative quantum computing modalities for, say, neutral atoms in analog mode for performing Boltzmann sampling? Just annotate machines.
Yeah. So with the Rydberg machines, I think it would be possible. But we looked in that, and it's really even less practical, because the way you read out the neutral atom quantum computers, that you basically destroy it, right? So you eject the one state and you keep the other, and you can see the readout basically you read out what you have not pushed out of your tweezers, right? So the cycling time when we looked at it was about 1 second. So it wouldn't, it really wouldn't be practical to do any kind of volume on this sort of machine. And we didn't see the path for this to have a drastic improvement, going down to microsecond level readout times.
So
And reassembly, because you have to reassemble the QPU basically from scratch every time for every sample. So that's the kind of a limitation there. It's also just engineering problem. In principle, the evolution could be very fast too, but we decided to go on with this as a first step. I'm open to exploring the further, but we have to see some kind of acceleration on those fronts.
Stella, you mentioned that it's trap ion because trap ion
for the material simulation, I do think there is a potential there. I think we could do this kind of analog simulation in a similar way.
So what kind of?
Because there is some research. So we are not really in the business of doing like the very basic primary research at TRIUMF. We're always trying to drive towards the application, which is of interest. So there is some basic research that suggests how to implement basically arbitrary lattices, how to manipulate the QPU to implement an arbitrary lattice. And I think that's key to, it's sort of an inverse problem, right? Like you have the lattice that you want to simulate. How do you control the QPU so that this lattice is implemented? There is some research on that, which we could build on if we have the sufficient scale.
Okay, thank you. Any other question? If no question, but in the interest of time, let's thank the speaker again.
Thank you.